Good morning, everyone. I hope that you guys are having a good start to your Friday. Today is that Friday, 7-Eleven. My understanding is that you can get a half off Slurpee at any I'm gonna sound like an ad here, but at any participating no, I'm not gonna sound like an ad because an ad wouldn't stumble like that. Let me think the words. At any participating 7-Eleven, you can get a half off Slurpee or a $1.50 Slurpee. I can't remember. Um, at any rate, that's something that you can do today. Today is our last day of new material. Um, and what we're going to do is we're going to pick up where we left off yesterday, which was at naming covalent compounds. And then we will talk about shapes of molecules, and then that's it. Monday will be a day in which we are reviewing. So Monday there won't be any new content, but it will still be a good idea to come by. Later today, one other announcement that is important to bring up. I got to minimize those deals just a second now. There we go. Nope, got to move that. There we go. Today I will be posting 5 assignments. And these 5 assignments will have the exact same due date. And that date is the day of the final exam. These 5 assignments, 1, 2, and 3, you can kind of consider those to be review sheets. Exam 1, review. Exam 2, exam 3, review. So these are just going to be, hey, here's a question and review. Here's a question based on this content, answer it and submit your answer. Then I've got 4 and 5, which are going to be more or less final exam review docs. Now, if I remember correctly, I got to look at my syllabus. And if you're thinking, oh my gosh, he doesn't remember his syllabus, yeah, sometimes parts of it slip my mind, and I apologize for that. On the syllabus, I have that there will be basically 1 assignment per week. These assignments, okay. What I'm going to do with these is there's basically 1 assigned per week. Here's all 5 of them all at once. They will be posted later today. What I'm going to do is drop one of these. They're 10 points apiece. They will be graded, but they are not due until the day of our final exam at 11:59 p.m. So if you want to wait until the very last minute, you can. I'm not going to stop you from doing that. What I would do is I would tackle this one in the next few days. An important detail about these is do not type your answers. If it asks you to draw something, I need you to draw it, as opposed to, as opposed to like Google image searching something and copying and pasting a picture. I need you to draw it. I need you to write it. Now, if you might be, or if you're thinking, well, how am I going to write that? You got a couple of different options. One thing is that you do not have to answer on the same page that the question's presented. You could get a blank piece of paper, write 1 on there, write your answer, and then take a picture of that whole thing and copy and paste it into a Word doc and export that as a PDF and submit that. And I will add on here PDF submissions only. Now, if you're someone who says, "Oh, well, I use a tablet for all my writing," that's fine. You can use a tablet to submit your answers, and you can write on that tablet. You can write on that document, and you can like scale it up, scale it down. The the thing that I don't want you to do is I don't want you to type it, and I don't want you to copy and paste things. Um, and so there you go. Does anyone have any questions about those 5 assignments? Okay. Well, then I'm going to go ahead and clear this, and I'll post an announcement about all this a little bit later today, whenever I post the assignments. What I wanted to get to in terms of content today is I wanted to jump into naming covalent compounds. So I'm going to say naming covalent slash molecular. And whenever you have a covalent or a molecular compound, you're talking about two nonmetals. And whenever you do that, what you need to kind of ascribe to or think about are your rules are going to be a little bit different. One thing that's going to be different is you're going to use prefixes. These prefixes are going to indicate how many of a particular atom there are present. So if I were to take these kind of blunt guidelines, I would say, okay, well, if I'm going to name this H2O, sure, we call it water, but we're going to start with the element that's listed on the left or the first one that's listed. And we're going to count up how many of them there are. I'd like to ask how many there are. You guys know that there's 2 hydrogens. So we would call this dihydrogen. Now, whenever I erase di, I'm going to rewrite it in just a second. This is the name of our element. There's no suffix or anything that's changed to the first element that's listed. The only thing that's changed is on the front end of the word, we write di to indicate how many. If water was instead 6, H6O, well, then we'd say hexa hydrogen, but it's not. Water is 2, so we say dihydrogen. Okay, now if we compare that to this right here, CO, carbon monoxide. The full name is provided right here. Well, I was just saying that we use prefixes for the first element that's listed. And you can see, well, there is no prefix that's provided. And the reason for that is your rules are, number 1, use prefixes. But there's a little bit of an exception. I'm going to say use prefixes for first element or first atom in compound. Oh, no, that's not what I wanted. First element in the compound. Okay. There is an exception to this rule. The exception to that rule is unless there is only one of that one atom of that element. So that's why we do not call this compound right here. That's why we don't call it monocarbon monoxide. We call it carbon monoxide. Okay. Now, that's also why we call this, or we start the name of this compound right here with nitrogen. There's only one nitrogen. Now, if there is more than one, what we see here, we say we use that prefix, just like what we're doing for water, dihydrogen. Okay. Our second rule, use a prefix for however many, many atoms are present of the second element. Okay, so I'm going to adjust these in just a moment. Dihydrogen, mon, oxygen. Okay, but this brings up, if you look down here at the bottom, we've got to drop the last three letters, or drop a couple of letters from our oxygen, our second element, and instead we use that IDE. Have we seen IDE before? Can you add to the chat one instance where we've used IDE? It can be a formula, it can be a application to a specific element or an ion. Add that to the chat. Well, we've talked about sodium chloride. So we've got that IDE suffix there. Okay, so we are again going back to that well of using suffixes. Now, oh, you know what? I got to add to my list 7/10/2025 final exam extra credit. Forgot to do that yesterday, so I've added that. That was 1 point. Okay, so 3 will be use dash IDE suffix. Suffix and prefix. Prefix comes before and a suffix comes after the root word. Okay, so these are our general guidelines. Use the prefixes and use the suffixes. Is there more to it than that? Eventually, yes. Are there common names that people use for specific molecules? Absolutely. Water. That name alone, or that name gives you no indication about however the atoms that make up that molecule. Do atoms make up that molecule? Absolutely. But we don't get that from the name. Now, what I want you guys to be able to do is take a formula and convert it to the name. Take a name and convert it to a formula. I want you to be able to do those things interchangeably. Now, as an example, here what we have is, what is the formula for phosphorus trichloride? Now, just because we've kind of looked at some other examples, we're going to work through this together. So we read left to right, and we're going to translate this left to right. Phosphorus has the symbol P. There is no prefix there indicating that we only have one of them. So the great thing about this question is, as long as you know that phosphorus is P, you actually already know that the answer is C, because there is only one example on here that has a single phosphorus. Now, I bring this up because K is a tempting option because K is the atomic symbol for something known as potassium. And I think that, or I know that this was written as kind of like kind of to trick you of sorts. At either rate, let's go ahead and work through this a little bit more. Say we can't remember if phosphorus is P or is phosphorus the weird one that has a K? I can't remember at the moment. What you can be able to do as a second approach is to at least cancel out A and D. Because A and D, the first element that's listed, there are 3 of them. So If this were triphosphorus, trichloride, that would be a different story, but that's not the case. So we can eliminate D and A. So that leaves us with trichloride. Okay, so now we're looking for Cl, and we're looking for three of them. Oh man, we're down to B and C. We were down to B and C when we canceled out A and D. Both B and C have Cl3 present. So at this point, if we can't remember if phosphorus is P or K, you kind of just got to flip a coin. And my tendency is to, or the way that I want you to think about this is think, okay, well, most of the elements that we talk about, carbon, boron, fluorine, their symbol is their first letter. So I always kind of think about that as a rule. And I want you guys to think about that as a rule, as like a reasonable expectation. I don't want you to say, okay, I need to learn the exceptions to the rule and then deduce what the rule is. No, learn the rules and then learn the exceptions. So if you learn the rules first, then you're going to end up at, okay, C is the correct answer. Because your rule, if your rule is the first letter is the symbol for the element, then P is the correct answer. Okay. Or sorry, then C or PCl3 is the correct answer. All right. Now there's another series of compounds known as polyatomic ions. Okay, so let's work from the end of this word backwards. Ions. An ion is something that, well, it's gained or lost electrons. Now, the important takeaway from this is that whenever something gains or loses electrons, well, it has a positive or a negative charge. So all of these things over here, I want you to notice about every single one of them is that it has a charge. Now, if you look closely at these, you'll notice that there's actually only two of them that have positive charges. So only two of them are cations. Now, when it comes to our polyatomic ions, one of the important things to understand about them is it's probably best for you to think about them as having a positive or a negative charge. And the reason for that is if you go into I like using this word, the minutia of where did the electrons come from and where did they go? Where do they come from, Cotton Eye Joe? Well, then you're going to kind of get lost in it, and it might be a little bit complicated. Now, whenever that happens, if you start out with this mindset of, okay, a polyatomic ion has a positive or a negative charge, that's going to set you in a good place. Okay, so I'm going to erase this right here, and I'm instead going to kind of extend my arrow to be ions have a positive or a negative charge. Then I'm going to go back to this, polyatomic, but I'm going to go with this word atom. Okay, so an atom is basically a thing that makes up everything. Polyatom. Well, that would be multiple atoms. So what I want you to do is deconstruct this phrase, polyatomic ions. And I want you to think, okay, a polyatomic ion is kind of an organization of multiple atoms with a positive charge or a negative charge. So multiple atoms with a positive or a negative charge. That is what a polyatomic ion is. If you go in with that mindset and if you approach it with that understanding, that's going to put you in a good position. What is important to know about these is that when you look at these names, let's go with nitrate. NO3 minus. Okay, NO3 minus nitrate. Let's see if I were to use my, oh, wait a minute, stop the press. Okay, so if I look at this and I say NITR, nitrogen. Yeah, okay, so this contains nitrogen. ATE. Huh? I mean, if I were to guess anything, I would say, oh, maybe this is nitrate. No, it's not. Nitrate is a polyatomic ion. It's nitrogen plus three oxygens with a negative charge. I'm going through all this because what I want you to know is that deducing the names, or it's you cannot use this set of rules to deduce what these names are. There's an entirely different or more involved set of rules to know what these names are. And if you were taking Gen Chem 1 or Gen Chem 2 or higher level chemistry classes, we would be using these so frequently that one, there's kind of an expectation that you have them memorized, but then two, you use them so frequently that the memorization becomes kind of like a second nature. It's almost like if you like baseball in time, you know how to calculate someone's batting average. You might not know how to calculate the average of the cost of bananas at five different grocery stores, but you can calculate batting average. Then, if you're in finance or in any sort of business field, you know what a P&L sheet is. You know what those things are just because they become second nature. There's nothing elaborate about them. Instead, it's just like, oh, yeah, of course I know how to calculate a batting average. Of course I know that permanganate is MnO4 minus. It's just something that you routinely use. And I'm sure and everyone has those, whatever their field of study or discipline or profession, they have those things. Now, with that in mind, when we name ionic compounds, what we're going to do is we're going to apply some of the rules that we have from naming ionic compounds and these names right here. So this list right here, if polyatomic ions are on your exam, you will be given a sheet of, or you'll be given this table. Now, what I want to do is I want to show you, well, okay, rather than go through these four examples, I'm just going to give you some examples. So if we were to come up with a compound that is NH4, that has a positive charge, that's a +1 charge, and combine that with, let's go with Cr2O7. Now, to put this compound together, the formula of this compound together, this is an ammonium ion and a dichromate ion. This is a +1 charge. This is a -2 charge. Another way to look at this is just like how we looked at ionic compounds. This is a minus, this is a minus. So Cr2O7 is rolling in with two negatives. One ammonium will neutralize one of those negatives. So what do we have to neutralize this second negative? Add it to the chat when you see it or when you think about it. To neutralize the second negative charge, what do we need? We need a second NH4. I'm sorry for being impatient and answering that for you guys, but I kind of worried about the question that I asked. Was it clear enough, sort of thing? So if we've got a formula that's made up of these three things, and I'm talking about them kind of as isolated things, NH4, NH4, Cr2O7, what we're going to do is we're going to say, oh, rather than writing this we're going to simplify it. We've got two NH4s. So I'm going to say NH4 and put in a parentheses. And then I'm going to add this subscript down here, 2, because that indicates that I've got two NH4s. And then what I'm going to do is I'm going to write Cr2O7. So this formula right here is the formula for a compound known as ammonium dichromate. And if you look at that and think, oh, okay, cool. I see that, okay, these are I'm applying those specific names. Ammonium is NH4 plus, but is this name right here for this formula? Add a Y or an N to the chat. Is that name correct? It is. It might seem like it's not because wait a minute, there's two ammoniums. Don't I need to have like diammonium? No, I don't. The reason for that is we don't use prefixes when we're talking about ionic compounds. So if I go back, our covalent or our molecular compounds, that's where we use prefixes. Ionic compounds, we do not use prefixes. So that would be ammonium dichromate. Now, if I were to make, let's say, NH4NO3, you might look at that and think, oh, well, I mean, putting that together, that is simply ammonium nitrate. Okay, so that's ammonium nitrate. Oh, wait, something in the chat. Okay, great. What did the 4/3 represent in the formula? I forgot. Are you talking about for the NH4 NO3? Okay, yeah. So what this, I'm going to go ahead and erase this stuff on the left-hand side of the screen. So I have a little bit of a space to draw. Oh, draw. Sorry about that, everyone. If I were to write out, say, NH4 plus, well, that 4 indicates the number of hydrogens I've got. So this molecule, if I'm going to draw the structure of it, looks like this. And then the 3, well, that corresponds to NO. We got 3 there. So the 4 and the 3 just represent how many hydrogens and oxygens, respectively, are in those two different molecules. Okay, so this compound right here, that's ammonium nitrate. That is the full name of this, ammonium nitrate. There's a couple of things to keep straight with respect to this. Okay. One thing to keep straight is when we write a polyatomic ions formula, we always write the ions separately. And what I mean by that is I wouldn't take this compound right here NH4 NO3. I would not write this as N2H4O3. Instead, what I want to do is I want to keep this thing, this NH4 and this NO3 kind of separate from one another because gives a more realistic impression of what they look like. Now, what we're aiming to do is we're aiming to make these compounds neutral. Your number of positive ions and negative ions, they cancel one another out. So I want you to be able to use this list right here and translate and transcribe a formula from a full name and a full name from a formula. Okay, now I am going to go ahead and jump on to the next slide deck. And this is the last slide deck of any sort of new material for this upcoming exam that is on Tuesday. This one's titled Molecular Shapes or Molecule Shapes. And this is basically taking a Lewis structure can I get a number in the chat if anyone's ever played a Mario game? Lewis structure and saying, what does it look like in 3D? Okay, now a letter in the chat if you have ever played a regular Nintendo game. I mean NES, side scroller, 8-bit Nintendo. Okay, great. The way that I always think about this is a Lewis structure is basically like an NES game where you don't see much detail. Mario has a mustache, he wears a hat. You actually only see like the right-hand side of his body and the left-hand side of his body. You never see him like facing forward. Then what we're going to be talking about is basically like taking that and saying, all right, well, what does this look like on a Switch? On a Nintendo Switch, you see, or a Switch 2, you see much more definition. You see the characters like, oh, the hat has this sort of contour, this sort of groove, so it gets this amount of light on it. So there's shadows here and there's shadows there. And Mario's really got one heck of a mustache. Luigi's got one heck of a mustache. Bowser's maybe not so scary after all because he's not that much larger than any of them. Maybe they could, get over it and just like find a compromise with him. Or he could just get over it and find another place to live. But that's just a different ordeal altogether. So molecule shapes are all about what does something look like in 3 dimensions. In order to understand that, we've got to have a good understanding of our Lewis symbols. We talked about these Lewis symbols where we put only our valence electrons around our symbols. We've got an oxygen atom with 6 valence electrons. How many total electrons does oxygen have? Well, oxygen happens to have 8 total electrons. Fluorine. Fluorine has 7 valence electrons, 9 total electrons. We talked about its electron configurations, or these 2 different atoms' electron configurations. There's a 1s2, 2s2, 2p6. Everything really wanted to get to a noble gas electron configuration like neon, because neon, as an example or as a representative of our noble gases, has a S2P6. And I'm just going to put an XX because argon has a 3s2, 3p6. Neon has a 2s2, 2p6. So their valence is full. They've got a complete octet around them. Now, we took that to translate that into, okay, well, how many bonds do these different things like to form? Fluorine, for example, has 7 valence electrons, and fluorine really likes to get, it likes to share one of those electrons to get to that complete octet. Chlorine has 7 valence electrons. It likes to share 1 electron to get to a complete octet. All of our group 7 atoms, they have 7 valence electrons. They share 1 to get a complete octet. Oxygen and sulfur, 6 valence electrons. They share 2 to get to a complete octet. Group 5, nitrogen and phosphorus, they like to share 3 to get to a complete octet. Carbon rolls in with 4 valence. I'm going to label this as VE, so the valence electrons, and it shares 4. It shares all 4 of those valence electrons to get to a complete octet. Because remember, if we have something like this, methane, just happens to be the name of this compound, CH4, that's 2 electrons. That's 2 electrons, 2 electrons, 2 electrons. This carbon in the middle has 8 electrons around it. 4 of them are being shared by hydrogen to that carbon. Here's our Lewis structures where we looked at water, ammonia, and methane. We had different numbers of lone pairs of electrons. Now, with that in mind, can you tell me how many electrons, add to the chat, how many electrons are represented by that line right there? 2. Okay. Can anyone tell me Y or N if they have a dog? Okay. For anyone who has a dog, is your dog an inside dog or an outside dog? I for an inside, O for outside. Okay. Okay. Um, I have 2 dogs. They live inside, but they should be outside dogs. They're way too big and they wrestle a lot. But that's that. They have lots of energy, and one of them has just this weirdest GI issue, gastrointestinal issue. It's like I feel like it's got too many generations of being a farm dog that it's like it really should be surviving on like garbage and rats or something like that, but we give it food, so then it has weird, excuse my language, but bowel movements. At any rate, that's not the point of the class. The point of the class is to talk about dogs and to talk about outside dogs. When I was a kid, we had some neighbors and they had an outside dog. And what they would do is they had this little, it was always just referred to as a rug. And it looked like basically 2 stakes in the ground. And between those 2 stakes, so I'm just going to make it like a capital T to represent like I think that it was actually whatchamacallit, a laundry line so they could dry their clothes out there. But they had this line that ran between these 2 big posts. And what they would do is here's the ground. Actually, I should change the color of the ground, but I'm not going to. They had this like leash here, and then they would hook their dog on it, their 4-legged friend. They would hook their dog on it. That's the dog's head. And the dog would run back and forth between those lines. Can it add a Y or an N if you can visualize that? Okay. Now, let's imagine just for a moment that these old neighbors of mine, they actually had 2 lines. And on those 2 lines, each one had a dog. And these dogs would run back and forth, back and forth. Can add a Y or an N if you can visualize that. Okay. Now these 2 dogs are the electrons. What are these posts? Tell me what these posts or these anchor points are. This and this. What do those represent in my model? I'm kind of translating this. You know, well, the line between them is the bond. So these circled things would be like the hydrogen and the oxygen, respectively. Does that make sense? Okay. Um, Now, where I'm going with this is that these dogs have kind of they had like a confined area in which they could run. They could basically run back and forth, back and forth, back and forth. And if you were looking at it from the top down, so here's the top down view of it. Here's a stake, here's the stake, one line, the other line. You know, the dog could maybe run out here and maybe there's some movement there. But basically, if I wanted to, you know, wherever you put a dog outside, it's going to run down the ground where that is. It's going to kill all the grass there. So let's just imagine that this right here, here's my post, here's my other post. I'm going to use brown to indicate where they've basically killed the grass because they're just running back and forth. These dogs are running back and forth. Can you visualize that? Give me a Y or an N if you can visualize that. Okay. Now, would you agree with me or would you grant me the idea that these dogs have this limited area because they're tethered to the line that connects this to this? Add a Y or an N to the chat if you can. Okay, cool. Now, that is basically what a bond is going to look like. These two electrons that occupy this space, they're not running on a straight line back and forth. Instead, they kind of have a curvature to them because they occupy this range of space. Now, if we've got, some people will also do this with dogs where they'll get a dog and they'll get a leash for it and they'll put a stake in the ground, a single stake in the ground. And what will that dog do? This is my stake in the ground. That dog is going to run out here. It's going to run out here. Would everyone agree with me at a Y or an N to the chat if they agree that this that I'm now coloring in is basically the path or the range that that dog is going to be in if it's anchored to a single space? Or, sorry, anchored to a single space. Okay. Now, with that in mind, these two electrons here, a lone pair of electrons, is a lot like this in the sense that this range left and right is going to be wider than this range that a single bond occupies. So the range here, where I'm going to label an X, is different from the range here, where I'm going to label a Y. So what I mean by that is the electrons that are bound to, or sorry, the electrons that make up a bond between two atoms, which is our dogs that are tethered on a line, they're not going to be able to run as wide as the dogs that have a single stake in the ground. They're only tethered to one place. Can you give me a Y or an N in the chat if you understand and follow that? Okay. So your key takeaway is that lone pairs of electrons occupy more space than bonded pairs of electrons. So a lone pair occupies more room, occupies more space than a bonded pair of electrons. Because that bonded pair, they've got two anchors. Because What is at the center? Tell me in the chat, what is at the center of a hydrogen atom? Or what's at the center of an oxygen atom? I'll give you a hint. It starts with an N. Add it to the chat. Nucleus. Okay. Now, there's two subatomic particles in the nucleus. What are they? Within the nucleus, the two subatomic particles are protons and neutrons. One of those will attract electrons to it. Tell me which one will attract electrons. Protons. So you've got a concentrated positive charge right here. Positive charge right here. So these electrons that are making up this bond, they're attracted either here or here. Here or here. Whereas then a lone pair of electrons, they've only got one place to be occupied or attracted to, in which case these electrons are going to be making a big old bubble like this. Can you give me a Y or an N in the chat if you follow that? Okay. So the question is, what we're looking at is, what is the space that these electrons occupy? The three-dimensional space. One way that I think about this, in addition to the dog examples, is I think about this as you've got your regular balloons that you inflate, and then you've got those balloons that you use to make balloon animals. The balloon animals, those ones are cylindrical. They look like hot dogs. It's balloon animal balloons are here. Regular balloons are here. And these are just, I'm using these are visuals for the space that these electrons could possibly be in. A regular balloon, oh, it's got a big, partially spherical shape. Electrons and a lone pair of electrons, they're going to be everywhere within that range. Balloon animals, they're more of a tube. So the area that they're going to occupy is a little bit more narrow. Now we use that information to look at this. Valence shell electron pair repulsion theory. Okay, VSEPR is what it's commonly known as. Let's break this down piece by piece. Add to the chat if you know what valence electrons are. Give me a number or give me a Y or an N if you know what a valence electron is. Those are our outermost electrons. Okay. Those are electrons that we talk about with respect to bonding. So those are our outermost electrons are what are known as our valence shell electrons. Does everyone follow me there? Add a Y or an N to the chat. Okay. Now, valence shell electrons, that's a term that we can kind of follow. These are the electrons that are in the outermost ring. Now, a pair, we are interested in lone pairs of electrons or bonded pairs of electrons. Are these electrons that make a balloon animal balloon, or do they make a regular shaped balloon? The lone pair of electrons make that regular shaped balloon, whereas a balloon animal balloon are the bonded pairs of electrons. Now, what do we know about two electrons? They're kind of like identical poles of a magnet. When you get these two things close together, what are they going to do to one another? Add it to the chat. Not quite. They're going to repel. If you get two magnets, the identical ends, and you bring them together, identical poles, if you bring them together, one of them's going to turn around. One of them's going to go away. One of them's going to be repelled. If you bring two electrons in close proximity together, they look at each other and they're like, oh, cool, 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 cool. Oh, you're negative. I don't like you. That's what happens. They repel one another. So we're talking about valence shell electrons, so our outermost electrons in pairs, either a bonded or a lone pair, and what do they do when they repel one another? Can you give me a Y or an N in the chat if you follow that? So we are interested in what happens when these electron pairs repel one another. What does that mean when it comes to the structure of a molecule? So we have these models right here. What we're doing is basically translating a Lewis structure to a 3D structure. So what I want you to look at is on the left-hand side, we've got HCN. We've got a Lewis structure. The Lewis structure for this can be constructed in the following ways. And I remember these numbers that I'm going to bring up just because I've seen them not a million times, several hundred times. I'm going to give you hydrogen rolls in with one valence electron. Carbon rolls in with 4 valence electrons. Nitrogen, 5 valence electrons. This whole molecule right here gives us a grand total of 10 electrons to draw. Now, to draw this structure, what do I need to know? What do I know? One thing that I know is hydrogen only wants to see 2 electrons. So H, dang it. There we go. Hydrogen rolls in with 1 valence electron, carbon, 4 valence electrons, nitrogen, 5 valence electrons. We got a total of 10 electrons. Hydrogen likes to have 2 electrons. So it rolls in with its own and then it shares. Now, when we look at all of these, our carbon is going to be in the middle. And the way that we know that is because carbon is less electronegative than nitrogen. Because carbon is farther to the left on the periodic table. So we'll construct this right here. We'll end up with a triple bond. Now, for these molecules that we're going to go over, I want you to know these as models and as examples. For your exams, you're not going to be expected to construct this Lewis structure. There are some molecules like water and carbon dioxide that, the ones that are presented here, it's good to know these. But I'm not going to throw something random at you and say, oh, construct this Lewis structure. This is our Lewis structure for HCN. Now, what we are interested in is the repulsion of pairs of electrons. So what we're interested in is this pair and these pairs. Now, we're not so interested in this lone pair of electrons. And the reason that we're not so interested in that lone pair of electrons is because it's farthest away from all of our other atoms. These two electron domains, the single bond and this triple bond, what are they going to do to one another? Are they going to attract one another? They are going to repel one another. You're absolutely right. And when they repel one another, that means that this hydrogen and this nitrogen, they are going to be as far away from one another as possible. They're going to be 180 degrees away from one another. That means that we can look at this Lewis structure and say, aha, well, that is a linear molecule. It makes a straight line as we go from one side to the other. Now, if we look at this molecule at the bottom, H2O, well, this structure right here, does that structure look linear? Add to the chat a Y or an N. With the H and the N. That's a good question, and we can look at a single bond and a triple bond as basically being equivalent. So to answer your question, yes, we would say that they would repel the same. Or do you mean the distance from here to here? So is this distance the same as this distance? Okay, the distance between or a single bond is longer than a triple bond, if that's your question. Um, so yeah, they are different, but they still repel one another. So the distance between H and N, that's 180 degrees. The distance this way from H to C versus N to C, you'd measure that in like nanometers. Truly, you measure it in a unit known as an angstrom, and that triple bond is going to be shorter than a double bond. Now, I asked if this molecule at the bottom, if water was linear, and Heather said, no, it's not. Heather's absolutely right. And for those of you who might have thought that, oh, it looks linear, the reason that it's different is because this bond and this bond, or sorry, this lone pair of electrons and this lone pair of electrons, those are like our regular shaped balloons. So in the lower right-hand corner of your screen, you see what this is. This molecule is considered bent because basically this lone pair of electrons pushes, and that pushes. This lone pair of electrons pushes, and that pushes. They're trying to occupy as much space as they possibly can and get away from those single bonds as much as they can. So that's why a molecule like water, where it has two lone pairs of electrons, would be considered a bent molecule. Now, what I want you to know are these different models. If you look over here at HCN, and we use lots of models and symbols to represent different things, which is one challenging part about chemistry, is that um, sorry, we are looking at this comparing the central atom to everything outside of it. So what we're most interested in, dang it, what we're most interested in is the carbon and everything that surrounds it, the oxygen and everything that surrounds it. And so we use something like this. A is going to represent our central atom. So could anyone in our first model up at the top tell me what A represents? Our central atom. It's a single letter. Okay. Now, for our second model, what does A represent? Okay. Now, we also we'll then say, okay, well, we don't really care about nitrogen being nitrogen or hydrogen being hydrogen for the purposes of this theory, of this modeling. So we say AX2. What does X represent in our top model? Spoiler, it's two different things. Perfect. Now, AX2, we use that at the bottom. Could you give me a Y and an N if you follow, or Y if you follow this AX modeling that I've done so far? The 2 tells me I've got two adjacent atoms, two adjacent atoms. Now, what is the difference between these two different molecules? Looking at our central atom. Does add a Y to the chat if they have something that makes them different from one another, the central atoms, not the identity of them. Electrons, you're absolutely right. How many lone pairs of electrons? Lone pairs, a pair. So how many lone pairs of electrons does water have on the central atom? Two. Perfect. How many lone pairs of electrons does carbon have in our top structure? Perfect. So I always like to think about this as the Axe body spray modeling system. So what we do is we say AX2 E2. It's the Axe modeling system. Now, we could do the same thing up here for HCN and say E sub 0. And that's effectively 0. So we just erase that. So we got AX2 E sub 0, but we just dropped the E. Does everyone follow that? Wire an N to the chat. Okay. Now, if I had something like this, AXE3, how many lone pairs of electrons would this molecule have? And how many adjacent atoms would it have from the central atom? Perfect. Perfect. Now, let me ask you this. Do you think that AXE3 is going to have the same model or the same geometry as AX2E2? Wire an N to the chat. No, it's not. It's not, because let's think about this. Do lone pairs of electrons and bonded pairs of electrons occupy the same space? Wire N to the chat. That's right. Lone pairs occupy more space than a bonded pair of electrons. So this AXE3 is going to look different than AX2E2. Now, this table right here shows us all of our, it's basically a summary of everything that we're looking at there. Now, to sum this up, this would be AX2. This would be AX3, AX2E, AX4, AX3E, AX2E2. I want you to know how this relates to bonded pairs and lone pairs, as well as what does that mean for the shape and the bond angles. So AX3 would be 3 adjacent atoms, 0 lone pairs, trigonal planar. That's the shape that this molecule makes. Notice AX2E and AX2E2 both make a bent molecule. AX4 is tetrahedral, AX3E is trigonal pyramidal. The good thing is you can look at this and say, well, how many domains does it have? And a domain, if we look over here, this is a domain, this is a domain, this is a domain, this is a domain. Domains are either bonded or a lone pair of electrons, a bonded pair or a lone pair of electrons. If something has two domains, the bond angle is 180 degrees. If something has three domains, the bond angle is 120 degrees. If something has four domains, the bond angle is 109.5 degrees. These are all models of what that looks like. Here's our lone pair of electrons. What is that lone pair of electron doing? It's repelling all of these adjacent atoms. Now, I want you to know this table well and be able to recall this well for future quizzes and such, which you have a quiz today that opens at 11 a.m. and closes at 11:59 p.m. tonight. Now, when it comes to bond polarity, we already talked about this with respect to electronegativity. Now, jump ahead there. I want you to feel comfortable with recalling this axe system and relating that to your bond angles and number of lone pairs and adjacent atoms. Now, with that in mind, does anyone have any questions about this? Yes. What can I help you with, Heather? For the HC triple line, does that count as one or three? Heather, that's a fantastic question. That actually only counts as one. So if I could jump back. So this right here versus this right here. These are both kind of considered equal in the sense of they are both single electron domains. So this is, I'm going to label it D1 for domain 1, and this is D2 for domain 2. These two things will repel one another kind of equally. These will repel one another equally as well. It seems a little bit weird because it's like, wait a minute, that's not right. But that's what it is. Okay. So now what we've got is we've talked about bond polarity, we've talked about electronegativity, and one important thing to know about electronegativity is that is going to have an impact on, yeah, actually, well, yeah, here we go. We want to be able to classify a molecule, count as one or three or what specifically. Count as one or three what specifically? This triple bond is one electron domain, and this single bond is one electron domain. Does that answer your question, Lynn? Okay, cool. So when it comes to defining the shape of an atom, we always want to be able to determine whether or not that atom is symmetrical or not. And when we look at a molecule, has anyone ever heard of the idea of like dissolves like? If you haven't, it's no big deal. I understand. Okay. Well, as chemists, one of the things that we do is we define things as being polar or non-polar. And when we do that, I'll give you a little bit of information. Water is polar. Has anyone ever heard of water referred to as the universal solvent outside of this class, if I'd mentioned it previously. So water is the universal solvent. The idea is that most everything's going to go into a solution of water. Now, water is a polar molecule. And if you look at it, you might be like, what does that mean? If we compare that to CO2, carbon dioxide looks like this. Each oxygen has two lone pairs of electrons. Could you tell me the geometry of a carbon dioxide molecule? Just kind of looking at my model that I put together there. So this is a linear molecule. Yeah, that's what I was looking for. It is carbon dioxide is linear. This domain and this domain, they're going to push each other as far away as they can. They're going to try to get away from one another as much as they possibly can. And that makes CO2 a linear molecule. Water, by comparison, so since CO2 is linear, it is symmetrical, it is a non-polar molecule. Water, by comparison, we've got these two lone pairs of electrons. And what are they doing? They are pushing as far as they possibly can against these bonded pairs of electrons. So whenever you think about something being polar or non-polar, what I want you to think about is, does it have at least one pair of or one lone pair of electrons on a central atom? If the answer is yes, that is a polar molecule, and it is therefore asymmetric. If something has only bonded atoms and they are all the same, it is considered a nonpolar molecule. And that's important because if you think about polar compounds versus nonpolar compounds, or if you've ever heard of a nonpolar compound, this will not go into water very well at all. So that's why you have, what if it has a lone pair, but it's not on the central atom? Can it still be nonpolar? It's a great question. It can potentially be nonpolar. Sorry. It can potentially be nonpolar. But sorry. But there's a kind of a range in how nonpolar it is or how polar it is. So if something has a lone pair of electrons, but it's not on the central atom, that would be considered slightly polar, but not extremely polar. Now, if we look at something like, so if it's symmetrical, it is nonpolar. If it is asymmetrical, it is polar. What we also want to account for is, what is that central atom bound to? If that central atom is bound to multiple of the exact same thing, then it is going to be polar. If it is bound to, or sorry, if it's bound to multiple of the exact same thing, then it is considered nonpolar. If it is bound to multiple different things, as we see here with NH3, one of those things is a lone pair of electrons, the others are bonded pairs of electrons. That would be considered a polar molecule. CH3Cl, well, that's a central carbon bound to 1, 2, 3 hydrogens and 1 Cl. CH4, central carbon, 2, 3, 4 hydrogens. This is nonpolar because it's completely symmetrical. So when it comes to classifying a bond as polar, we want to look at electronegativities. We want to classify a molecule as polar. We want to look at, is that molecule symmetrical? Yes or no. Does that make sense? Okay. Well, that is actually the end of today's slide deck. Um, if anyone has any questions, they are more than welcome to hang around. I'm going to stop my share here. So I'll be here to answer any questions that you may have. Other than that, though, I'll see you guys on Monday morning. And Monday is going to be a review. Look out later today for the posting of the assignments for this or for all of the semester. Remember, all of them are due on the day of the final exam. However, assignment one would be good to do kind of as a review for exam number one. Doc two would be good for exam two. Document three would be good for exam number three. All right. Well, I hope you guys enjoy your weekend. If anything comes up,